So this is a conservation of energy problem. So we're going to begin with KO translational plus KO rotational plus UO plus work equals KF translational plus KF rotational plus U final. All right, so that includes all of the types of energy that we could have before, at a starting point and at some later point. In this problem, we're just talking about a tennis ball that's rolling down a hill. And now here's how I could change this problem to be different. This is a tennis ball. So they say treat the tennis ball as a thin-walled spherical shell. Well, I could have on the test a baseball, which you would consider a solid sphere, not a hollow sphere. All right, so that's how I could change it. I could have on one version of the test the tennis ball, and on the other version a shot put or a baseball, something else, where you would just have a different formula for the moment of inertia. Everything else would be the same. So in solving this, let's get rid of what we don't. We actually have, what can I cancel out here? What's that? Good. In this one I can cancel out original kinetic energy. So that means I'm eliminating both KOT and KOR. That's good because there's a lot of stuff there. What else can I eliminate? Work. Right. I can eliminate work because there's no work between the original position and the final. So all those are zeros. One other thing can cancel. UF, because I'm going to call this my ground level because that's going to be above it. So I start with a potential energy. Now, even though it goes down below that, all that matters is where do I begin, where do I end? What the change in height from there to there. So that means that my final U is 0. So all of those are 0. Makes it a lot easier. I don't have all these different terms. Yes? Well, work would be the reason why the energy on the left side is different than the energy of the right. So, for example, if there was some engine on the tennis ball, or I was pushing it down so that I was applying a force through a distance while this was also happening, or like riding your bike. If I just was rolling my bike down a hill, then it would be no work. But if I'm pedaling while I'm on the hill, then that would be work, so that my final energy would be different than my starting energy. Okay, so now we have on the left side, the only energy we have is mg times the original height. So all of the energy comes from potential energy. And after, we have two types of kinetic energy. So we're going to have 1/2 mvf squared plus 1/2 I omega f squared. So what I'm going to do is just like what I did in the last problem. Notice again, they didn't give me the mass of the tennis ball. So it must cancel out. If I do my substitutions, I'm going to have mass in every term. So on the left side, I'm going to have mgho. I'm still going to have 1/2 mvf squared plus 1/2, and here's where I have to do my substitutions. So for I, I'm going to write the moment of inertia for a hollow sphere. And what's that formula? Which is different than a solid sphere. 2/3. So it's 2/3 mr squared. And then I can replace omega with v over r. So there's my equation. Now let's cancel out all the stuff we can cancel. So I can cancel the mass out of every term. I can cancel over here. The r squared cancels the r squared. And while I'm at it, I can cancel that with that. So just like what I did before, what is my least common denominator in this problem? 6. Good. So it's 6. So I'm going to get 6 GHO is going to equal 3 VF squared plus 2 VF squared. And I'm looking over there and I don't see the F, so let me put that in. This should be VF. And then the unknown, let's see, the unknown, well, we're solving for the final velocity, and then from there I could figure out the range. But like I told you, I mean, I can solve it through and do the projectile motion problem, but on the test, the unknown is going to be the final velocity for this. So I'm going to get 6 GHO. I can combine like terms, so I'm going to get 5 VF squared. So divide both sides by 5 and take the square root. So VF is going to equal the square root of 6 GHO divided by 5. And then you plug in the numbers and you'll have the answer. So, well, you won't have the answer that I gave because the answer was for the range, but you would have had to get this first. And so you're going to have 6 GHO over 5. So I'm going to put in 9.8 meters per second squared. And then for the height, I'll put in 1.8 meters. And solving that, and what do you get for the final velocity? 4.60. Now, again, that's not the actual answer in the problem because then they want us to take it a step further and solve a projectile motion problem where that would be the original velocity. So if I look back up here, if I know the original velocity and I know the angle, all right, I'm not going to go through this because we need to go through the other problems. So if I know the final velocity and I know the angle, I can figure the VFX and the VFY. I know VFY. I know, which actually VFY would be VOY because the motion at this point that would begin the motion for projectile motion and it would end over there. So the answer that I have down here would be, although I'm calling it VF because it's the end of the first part of the trip, it would now be the original velocity here. So that 4.60 meters per second would be the original velocity, and I have the angle. So I'd be able to get VOX and VOY. Well, I also know, VOY, so I know VFY because they're ending at the same level. So I would know VOY, I would know VFY, I know AY is negative 9.8 meters per second squared. I could use those facts to solve for time. I could also use SY being 0. So, I know everything that I need to solve for time. And then if I know the time and I know the VOX, I know AX is 0, I could solve for the SX. The range would be the displacement in the X direction. But I just want to talk it out rather than do it because this is where the problem's going to end on the test. All right? Any other questions?